Hello guys, today I would like to introduce a brief subject, very important in physics. It's a very common set of equation and that are ubiquitous in physics, so it's best to at least have a look at them once. And it will be harmonic oscillator. Okay. Oscillator. Okay. And I will do two videos on this. One classical mechanic, which is the one today, and the other one mechanic, and the other will be quantum. Okay. So that would be, of course, I will try to give an idea of the differences and the similarities. At least we will have another bit of the puzzle to try to grasp a little bit more about quantum mechanics. But today I will focus on the classical part, which is anyway essential. I think very important to at least have a look and have a feel for it with a couple of examples that I will try to. Okay. So what is an harmonic oscillator? An harmonic oscillator is anything, a quantity, a physical quantity that we can measure, and in essence, in a very simple terms, we can say that this quantity, let's call this f of x. It's a quantity that depends on, let's say, time, to make life easy for me. This quantity, I will give example. It could be the motion of a particle. I will deal with motion of a particle. It could be energy, it could be electric field. For example, in an electrical circuit, it could be the voltage or the current. Anything. So think about something that you can measure in time, and the graph of which could be an oscillation, a sinusoid, a cosinusoid, like a sinus of t with some constant, or a cosinus, doesn't matter, a combination of a sinus and cosinus, and also something a bit more real than just a sinusoid oscillation, which can be an oscillation with some damping. So basically an oscillation that decays in time. Okay, this is mostly common because basically anything shows some loss of energy. Okay, meaning that if the system loses energy with time, the oscillation, because it has less energy to spend in each cycle, will decrease the amplitude of the oscillation. Okay, so this is damped oscillation, and this is just harmonic. Okay, the idea is then to refresh. I mean, we don't have to go through the again to the detail of what a sinus and cosinus are, but maybe just a quick refresh, just the basic. So you have the quantity. Usually we normalize it, so we don't normalize it. We have an amplitude and sinus of omega t. Okay, terminology, a little bit of terminology. A is the amplitude, meaning that is how wide, suppose it goes from here to here, the oscillation. The amplitude is this one. No, actually the amplitude is just this bit here, just half of it, because that goes from minus A to A. This is A. And the frequency basically is a measure of this distance here, because this distance here is 2 pi over omega, or actually, yeah, 2 pi over omega. Okay, so this is the period. So just to let you know, omega is the frequency, and this as a unit of measure of hertz. You don't talk often, I don't talk often about unit of measures, but as you might imagine, in physics, unit of measure is essential. You need to understand what is the physical constant that you are dealing with, and also the scale at which the process is happening. So having in mind the unit of measure is essential to understand the process and to grasp the phenomenology, but also to get the number right in the end. So frequency, so it's hertz, and it's 1 over time, 1 over second. Okay, and if you think about it, 1 over second times second here is nothing. It simplifies, meaning that this is a number, as it should be, because the sinus usually takes in an angle, which can be radians or degrees. It doesn't matter. You can convert them with a simple proportion, like for example, pi over 180 times x. This is the conversion from radians to degree, or vice versa, 180 pi over x, and this is the conversion from degree to radians. It's just another way to measure the angle. But what's important is that whatever it's in the sinusoid, it must be a number without unit, and this is why you have frequency times time. Also, the amplitude carries the physical dimension, so the unit of measure of your system. So in this case, f of t could be energy, and A will be expressed in joule. If it's space, displacement will be meter. If it's, I don't know, a current, it will be ampere, and so on. So the amplitude will carry the actual dimension of your physical system, while the frequency will carry the dimension of 1 over time. Okay, so this is just a quick recap, but I want just to do a step further. So we talk, this is mostly sinusoid, so the amplitude never changes with time. So it's always between A and minus A, and this is fine. Now, how can you get an amplitude that decays in time? Okay, that's quite easy if you remember that an oscillation can be written as omega, let's say omega t plus e to the minus omega t. Okay, and there are two contributions here, right? Okay, because this is the sum of two complex number, which is basically 2 times the cosine of omega t. But a complex number, if for just a second, I will give you the reason, the equation why this can happen, but this is a complex number, and in principle omega could be a complex number as well. Okay, so suppose that omega is now a complex number, not real, so we put z, and then we get to do another step. So let's cancel this one out, just focus on this one. So by the way, it's clear that if we have e to the I omega t, and we take the real part, is also cosinus of omega t. Okay, so just bear in mind that a complex number already carries the oscillatory behavior inside without summing it to the complex conjugate, as we did before. It's in the definition of a complex number because it's cosinus omega t plus I sinus omega t. So the oscillatory part are inside the complex number. Okay, so we need just to extract them whenever we need. But now, for the sake of argument, the moment is just math, but believe me, there is some physics behind, and we'll see some equation, hopefully. So suppose we get a complex number, so we have I, and then we have A plus IB, which is Z, is the complex number, times T. And this, of course, creates e to the IAT times e to the minus BT, okay? Because we remember that I times I is minus 1, so this times this will be minus 1, which is this minus 1 here, okay? And B is there. So what is this? As you can see, if we allow for a general complex number, very general complex number, an oscillatory behavior with a complex frequency, let's say, if it makes sense, we get this, we get the simple complex number with a standard oscillatory behavior, because now A is a frequency, is a real number. So if we take the real part of it, or we sum it with a complex conjugate, doesn't matter, let's take the real part, we will get e to the minus I, sorry, we will get this e to the minus bt cosinus omega t, because the real part of this exponential, which is real, is the same, and the real part of the exponential with the oscillatory behavior is the cosinus. Now, this is clear. We never discuss about product of function, but we can just simply do point by point. We superimpose the two functions, and then we see what happens, and then we will see that this should lead us to a damped oscillation, very much the same that I described in the picture above. So let's see if I can do this quickly. So we have our Cartesian axis, x and t, whatever that p, y, let's say, and then we put the sinus in, or the cosinus. This is the sinus in this case, but it doesn't matter. And then we put the exponential tail, so something that decay like an exponential, something like this. And then we do the product of the two, meaning that your oscillation will go up and down, and then it will touch, and then it will go, be basically, what I'm saying is that the oscillation that you get out of it will be bounded by the exponential decay, but with the same periodicity. So the periodicity is still a over 2 pi over a, but the amplitude is decaying. As you can see, with time there is an exponential that reduces this arrow here, okay? And this means that your system is damping, is basically dying over time. It loses energy. Okay, so enough with the setting up. I think what I want to show you now is how do we what are the equations that we need to get this kind of oscillations. And then I think in the second part of the video, if it's not too long, I will give two simple but very well-known example where this oscillation actually takes place. And then in quantum mechanics, the quantum mechanics video, I will go through the energy description of the same thing, which is something that I'm skipping on purpose because I want to take a bit of time to do that. But let's start with the equation of motion, which is F equal, in this case not m, usually we deal with F equal m times a. In this case the equation of motion is different, is what is called Hooke's law, for example, or anyway, it has many names, but this is the, so what I'm saying is that this is the formula is always F equal to m. Okay, yes, of course. On this side we have m times a, but the force is actually has this shape here, okay? And this is the displacement. So m times a derivative, second derivative over time of x. This is the acceleration because this is the position, and then minus k, which is a constant, which is called in this case elastic constant, and this is the position as well. Okay. K is elastic constant. What does this mean? This means that the bigger so suppose, so the easiest example that, but let's not do the example now. Let's think about the equation. That means that if the displacement is large, big displacement, the acceleration will be large as well, but with a minus sign, meaning that the more you try to escape from your initial position, x naught, this is x, so the more you try to escape, the stronger the force will pull you back into the position. And of course, this goes the other way around. If the force is pulling towards the initial condition, when you exceed it, you will start to enlarge again x in the other direction, meaning that the force will again pull you and change sign again, and then drag you back towards the origin again. This is already kind of tell you that your mass is moving from one point to another, passing many times towards the middle point, essentially. And if you think about this, is like what happens when you have a pendulum, something that is actually periodic, right? Because it's oscillating from very far away and then slowly down to the minimum and then up again and then down and up and down and up, so forth and so on, so forth. So okay, but okay, this is a hint that the equation is actually suggesting, but let's see if we can actually extract our oscillatory behavior. Okay, so let's see if I can convince you that we can find the equation. Okay, of course, if you look at the video on sinus and cosinus and derivative, we know already how do those function behave under derivation, because if we derive the sinus over time, we get something like x cosinus of omega t of xt, and if we derive again, we go back to the sinus with a change of sign. So as you can see already, to sin, we know already that the sinus is a good solution, because if you differentiate it twice, you get the same function back, which is exactly what we are asking here, right? What is the function that if you differentiate twice, you get it back? Usually, when we did the differential equation video, we have something like this, f of x, okay? This is the standard template. You have the derivative of a function, and then you get the function again, or a function or a combination of functions. It doesn't matter. In this case, it's the same function, okay? And then you have to solve for the function. In this case, the function is x. It's just the motion, the displacement, and the derivative is the second derivative. But you want to get it exactly back when you differentiate twice. So sinuses and cosinus will be fine. Sum of sinuses and cosinus will be fine as well. We can cast it in the standard form, let's say in this other fashion, which is more mathsy, in the sense that at least we have numbers without dimensions. Okay. I mean, these have dimension, by the way, because it's displacement over time second. This is an acceleration. Okay. Now, this is the equation that we want. As you can see, it's quite easy. We have a solution if you want. But I want to remind you of two things. First of all, let me do it a bit more general. Okay, so first of all, this is the equation that we want, and let's do a step back. In general, this equation can be solved, and I will show you why, by this kind of yes, AT or BT in general. Okay, if we put this equation in this differential equation, we will find some constant a, b, small a and small b, which will satisfy this equation. Let's see why this might happen, because and then I will remember that we have this equation here, which is derivative second over time of x minus k over m x. This is our equation that we need to solve. But let's differentiate twice this equation. Okay, we get f of t. So the first one, we get the first derivative. Let's do the first one, and then the second. So the first derivative will be I a e to the I a t plus minus I b b e to the minus I b t. Okay. Now this is not quite the same as f, as you can see, because there is an I, there is an a, there is some, we need to, but still we can find in this case some solution for this equation if we play with the complex number. But this is not what we want. We want another derivative over time of this equation, which brings another I down, so meaning that we get minus a squared a e to the I a t, minus minus is plus, with a minus is minus, b squared b a to the minus I b t. Okay, now we can see this is the second derivative, and now we can find we can start to ask what's the initial condition of the velocity and the position. So we need to block some of this component. So suppose that initial condition is x0 is 0 at time 0. We know that we need to fix some of these parameters such that that will be satisfied. So for example, we can plug in 0 in this equation here on the top, and then we get that, for example, a plus b must be equal to 0, meaning that these two numbers are the same with a change of minus. Okay, so we can do this, for example, and this is already a step, because we know that the position is 0, and this means that the oscillation starts from here and not from the top, for example. And then the first derivative could be, we need to find the derivative of time, so velocity at time 0, suppose is whatever number it is, suppose is k, I don't know, and then we use this one to this equation to fix basically a and b, small b and small a. And okay, I don't want to go through all the calculation because it could be long, but what I'm saying is that in the end we have enough equation to solve for this structure, And we can see that, for example, if we start with 0, an oscillation like, let's say, let me guess it, but this is b square, so we can do, for example, a, this is our amplitude, and sinus of, and this is, by the way, this is the square root of a, so a omega t. Okay, so, and a square is kappa over m. Okay, if we plug back in the numbers, we will find that a square is k over m, and this is fine. And then we can see that this equation actually do solve for this by changing the initial condition. For example, if we put 1 here, or a actually, we could get the cosinus instead, or we could, and also we could play with the phasing here if we have a different condition here, a different timing, or the velocity is different. So what I'm saying is that this is a very general solution for the harmonic equation, because those are two complex numbers which are harmonic as well, and then and this exact same equation leads to the harmonic solution that we want. And by the way, so this is exactly an elastic force, which means that attract the mass to the center point as anytime that you want to the force act to somebody acting to move it away from the point. So, for example, this is what happens when you have an electron orbiting. No, sorry, not an electron. Anyway, sometimes. Anyway, in some assumption, but it doesn't matter. Let's think about the pendulum, which is easy, or a spring. Okay, these are the two examples that I want to make, and I will just link to the Wikipedia description, which is much tighter than what I can do. But the example is a pendulum with mass m, and the oscillation is theta, or a mass attached to a spring which is compressed and attached to a wall. This is the distance dx. This is the mass. Okay, in both of these cases the equation is very similar. So in the first one, the derivative of theta, which is the angle, is proportional to theta, and a is g over l, where l is the length of the rope, and g is the constant of gravity, because that's the force that is acting on a pendulum, because it's the gravity that's pulling down the pendulum. And the mass is the same that I want to show you before. Sorry, the two dots is just maybe silly, and this is x, the position along the x-axis, and k is the strength of the spring. The larger is the string, the shorter will be the oscillation, and so on. But okay, those are two very simple examples, and those motions are indeed harmonic if there is no friction. So in fact, this is the second bit that I want to quickly introduce, which is what happens if you have frictions, or you have a force, in fact, that depends on velocity. That means that the equation of motion is dx squared over theta squared plus some constant over the velocity equal to minus kx over m. Okay, we introduce the equation. You see is the same as before, apart from this term here, which means that the force as a contribution that also depends on the velocity, meaning that this can be captured by friction or some loss in the system that happens every time. Okay, so this could be the friction here, it could be air, it could be the friction on the post that is holding the rope. It's anything that introduces some loss of energy while the thing is moving. So every time, depending on the velocity, the force will change point to point. So it's not constant, the force. Okay. So what I want to say is that this can I don't want to drag it too long, but what I want to say is that these equation, if you plug in the same above FDT over, you will see that the actual solution for this equation needs to have an exponential inside. So there will be an oscillatory term anyway, which derive from these two bits basically, because this is still true. But the first derivative is something that brings down this exponential. And if you think about this, it makes sense because dx over dt is equal of x, ax. Exactly, this is the solution of the exponential that we already saw, leads to f of x, f of t equal e to the minus or plus or minus at, depending on the sign here. This case is a plus or a minus. We do this. Okay, so as you can see, the linear term with the velocity has this solution, and the harmonic term with the acceleration has the oscillatory solution. Why this then ends up in a product of the two and not on the sum, this is we need to basically prove it step by step. It's a bit maybe tedious, but not that long. We can just plug in f inside this equation, maybe just put b equal to 0 to simplify the thing, and you will see that a must be complex in order to solve this equation, meaning that, as we saw in the previous slide, if it's complex, you get the damping, exponential damping that we need. Okay. Okay, so I hope this is somehow clear. I will recap it with a couple of slides, but basically what we touched on is harmonic oscillation due to a force that is linearly dependent on the displacement, and this leads to oscillatory behavior with constant amplitude and fixed frequency. And this is, for example, a pendulum, the motion of a pendulum, or the oscillation of a spring, and actually the motion of many atoms in crystals around the equilibrium point, or even the oscillation of a laser, or other. I mean, it's ubiquitous in physics, basically harmonic oscillation. But it can be also anharmonic, so damped, meaning that there is some loss of energy, and this is due to some friction or some damping due to external forces that are not harmonic, so linearly dependent on the displacement with the velocity, and this leads to some damping, so an exponential decay that kill the oscillation over time this way. And that's the reason why, for example, a pendulum at some point will stop if you don't keep putting energy into the system, or many other, for example, even a spring will at some point stop oscillating or bouncing back and forth. Or a ball, when you drop a ball from some height to the ground, it will start bouncing. This is a harmonic oscillation if there is no friction or if there is no loss of energy. But we all know that when you drop a ball, at some point it will stop, and this decay is essentially an exponential decay. Okay, so this is what I want to say about harmonic oscillators with an S, many of them, and I hope I will make it clear also for the quantum application, for quantum case, and we will see some differences and also in the approach of how we deal with this stuff. Okay, thanks a lot. See you next time. Have a good day.